Okay, and number 2, they give us a table, and in that table, it says that the values of the function and the derivative are given at selected values of x, and it says if f prime is continuous on -2 to 2, we want to know what is the average value of f prime on the closed interval -2 to 2. Well, ultimately, recognize that it's just an average value problem. We know in general the average value of any is just going to be as such. The integrand, notice I put as f prime because we want the average value of f prime. Okay. So the issue here is can we come up with an answer for that? Well, let's start with the 1 over b minus a part. Our b minus a in this case is we're going from -2 to 2. So that part would be a quarter out in front. Okay. And then we need the integral from -2 to 2 of f prime dx. Now, key question is though, do we know f prime? And because if we knew f prime, then we could find the antiderivative and we could plug in our 2 and -2 and do the subtraction and get an answer. True? But do we have an equation for f prime? No. Okay. But what do we know about an antiderivative of f prime? What would be an antiderivative of f prime? F. So ultimately, wouldn't this be f of x then, evaluated at 2 and -2? Remember, the fundamental theorem tells us all we need is an antiderivative. Right? So if it's a definite integral, we can find an antiderivative of f prime, which is f, and evaluate it at 2 and -2. And so ultimately we get f of 2 minus f of -2. And what do we know about f of 2? That's right in our chart, isn't it? F of 2 is what? A? Okay. F of -2?
Oh, it was E, sorry.
So E you said?
Yeah.
And f of -2 is A? So ultimately the area under that curve then is E minus A. And the average value then would be a quarter times E minus A. And ultimately that matches up with which one? It's letter B.
Where did you get the quarter? 1 over B minus A.
1 over B minus A. So we want the average value of a function is 1 over the length of the interval times the area of the curve over that interval. That is the average value of any function.
Just remember the A's and B's.
Trust the calculus. Don't get bogged down with what symbols they use, letters, smiley faces, Christmas trees, whatever the case may be. You still trust the calculus. What else? Go ahead. Number 3, we got f is a continuous function. They tell us f of -5 is 3. F of -1 is -2. If f of x is equal to 0 for one and only one value of x, then which of the following could be the value of x? Okay. And ultimately, again, keep in mind that picture-wise, if you visualize this, we're at -5, 3, and then now we're at -1, 2. Okay. If this is a continuous function, okay, and again, we need to be able to name these theorems, because if this was in the free response part, we need to be able to name the intermediate value theorem here, because that's what we're dealing with here, is when we're going from one to another, they're trying to get us to see that there's going to be a 0 in between there somewhere.
Shouldn't it point be at
-1,
-1?
-2, sorry. Either way, below the x-axis is the important part, I guess, in this case. But between -5 and -1, what must have happened? We went from y value 3 to y value -2. The intermediate value theorem guarantees that we must have crossed every intermediate value between 3 and -2, which includes the main one, which is 0. And so ultimately we would have to have a 0. It would have to be between -5 and -1, so therefore the only possible choice here would be what? Be -2, which would be B. Okay. Right. Again, could there be zeros at those other ones? There could be, but does the mean value or intermediate value theorem guarantee it? Intermediate value theorem guarantees that between these two x values, okay, that every intermediate y value is attained. So everything between -2 and 3 in the y direction is going to be hit, including the most important one, which is 0. What else? Yeah, let's see. Number 6, we have the integral of radical x times x plus 2 dx. So let's go through our sequence that we know so far for dealing with integrals. We know that we first ask, is it a known derivative? And the answer to that would be nope. Okay. Then if it's not a known derivative, is there anything we can do to simplify the argument here so that it is something we can anti-differentiate? keeping in mind that the most common and easiest functions for us to anti-differentiate are power functions. So anything we can do with that to make it nicer?
X can be raised to the power.
And if we do x to the 1/2, which is what this is, and we distribute this, wouldn't x to the 1/2 times x to the 1 be x to the 3/2? If I distribute here, and then it would be 2x to the 1/2. So with that, would my integral become much simpler because now it's just a power function? You know, you could have tried substitution in here, but nothing you substitute is going to make all that stuff go away. So that's obviously not the approach, and there's really only a finite number of ways we can do it. So, you know, I'd always approach it as, is it a known derivative? If not, is there anything I can do to the integrand to make it so that it is a known derivative? Okay? And if it is, then let's go from there. If it's not, then maybe substitution comes into play, etc. So ultimately we get x to the 5/2 over 5/2, and then it'd be 2 x to the 3/2 over 3/2. And of course they're going to give us a simplified version of that, I assume, right? So this would be 2/5 x to the 5/2. They put them in, actually they didn't even put them in radical form, did they? So 2/5 actually would be, and this divided by 3/2 times 2/3 would give us 4/3 x to the 3/2 plus c. So it corresponds with letter D. That's base here. What else? Right? Okay, now number 4, we have tells us that if f of x is equal to 2 plus 3x all raised to the 4th, then the 4th derivative at x equals 1 is the following. Ultimately, you know, this is a fairly simple function to work with here, so if we just find the 4th derivative, we can hopefully see a pattern develop here, maybe. We know that if we use the chain rule here, that's going to be the first derivative, but that's going to be, of course, times 3. And as you can see, that the answers that we're getting here are patterns, if you will. And so if we notice that I didn't simplify that. Okay, if I keep this as is, if I do 4 times 3 now, 2 plus 3x to the 2 times 3 times 3, we're going to be multiplying it by another 3. And then if we do that same thing for f triple prime, we're going to get 4 times 3 times 2. And what pattern are we noticing out front is starting to develop? This looks like a what? Factorial. So if we do that one more time, we're going to get 4th derivative. 4 times 3 times 2 times 1 times 2 plus 3x times 3 times 3 times 3 times 3. Okay. Keep in mind that that's to the 0 this time.
Why are you multiplying something times by 3 on the outside?
The chain rule.
Derivative of the inside?
Derivative of the inside. Yeah.
But why are you multiplying 3 times by 3?
Well, we had a chain rule here. When we did the first derivative, we'd have to multiply by 3. When we do the second derivative, there's another 3 inside.
But I thought that one moved up front.
No, this out front one comes from the power.
Oh, okay.
The front parts are coming from the power, as the ends are coming from the chain rule. Okay. All right, and so bottom line here is, again, if we follow that chain rule here, we're gonna have, this is gonna be to the 0. So what is this quantity right here, really? It's just 1. So we wind up with just simply 4 factorial times 3 to the 4th. Turns out to be letter C. What else? Victor?
Number
5 says, where do we have a relative minimum here? We have x to the 4th minus 8x squared. Well, where do we have any relative maximums or minimums when what happens? The derivative equals 0. So if we did 4x cubed minus 16x, we set that equal to 0. We took out a 4x, we'd have x squared minus 4. So we have 0 here. This would be plus and minus 2. Our 2 solutions to that. So if we make our points on our number line and do our first derivative test, we can see which one of those is a maximum or minimum, or if any. So anything left of -2 here, like -3, would make this positive. Minus 4, 9 minus 4 would be positive. But here it would be a negative, 4 times -3. So this would be a negative times a positive, that part would be negative. -1 would give us negative here, which would be positive. 1 would give us positive here, negative here. 3 would give us positive here, positive here. And so ultimately this -2 right here would be a minimum, decreasing before it, increasing after. Maximum at 0, min again at 2. And question says, at what values of x does it have a relative minimum? So the answer would be -2 and +2, which would be D. Questions on any part of number 5? What next? Yeah? 7, they ask us for the limit as h approaches 0 of x plus h minus x in absolute values, both of those. Alright, and so you might have asked me at the time, remember when we did limits, when we used the limit definition to find derivatives, we said, do we always have to do that now that we know these nice rules? And the answer is no, not necessarily, but we do need to recognize that this is the limit definition of the derivative. Okay? We have a y value minus a y value over h, which ultimately came from an x plus h minus x, if you will. So this recognizes that this is a slope, recognizes it's a derivative. Question is, what did we put our x plus h into and our x into? What function are we dealing with here? The function is the absolute value function, isn't it? Okay. So ultimately, what is this expression? It's just the it's the derivative of f. Okay? And we want to know what's the derivative of f at x equals 3. Well, knowing that this is an absolute value function at x equals 3, 1, 2, 3, what's the derivative right there? 1. So therefore it should be letter C.
And how do you know it's the absolute value function? You just know.
Because again, in general, the limit definition is the limit as h approaches 0 of f of x plus or minus h. I guess it really doesn't matter, but ultimately, do that. Remember, we're taking a point that's close to x value, right? Minus x value. This gives us a difference in y values. The bottom came from x plus h minus x, which is just h. Okay? And ultimately, this is our general formula. So what goes on the top? What do we put our x plus h and our x into? We put it into a function. So another alternative, what if we had x plus h squared plus 1 on top minus x squared plus 1? What's the function here in this case? It'd be x squared plus 1 would be the function, because we put our x plus h into it and then we put our x into it. Okay? So you got to recognize what the function is by what have we done here with the x values on top. What did we put them into? Okay? We put them into absolute value. That means the absolute value is our function. Good derivative definition question, because you don't actually have to do the algebra and arithmetic it takes to actually do any math. You just need to recognize that it's the absolute value function, and its derivative at 3 is 1. The only two possible answers here would have been 1 or -1, because it would have been on the other side, it would have been just -1. Next.
8.
8 says that we have y equals x to the 4th plus bx squared plus 8x plus 1. It says it has a horizontal tangent and a point of inflection for the same value of x, and if that's the case, what has to be the value of b? So once again, if we have a horizontal tangent, then we know that what has to be the case? Derivative has to equal 0. So let's find that. So the derivative here would be 4x cubed plus 2bx plus 8. So we would know that at this value of x, we would have that be a true sentence then for our problem. We also know that there's an inflection point, which means that what else has to be true? Second derivative has to equal 0. So second derivative would be 12x squared plus 2b. And if we know that 12x squared plus 2b has to equal 0, okay, why can I not solve either one of these equations by themselves? Because they both have what? Both have two variables. However, I could easily solve one of these for one or use substitution. I could find both, couldn't I? We know that these two sentences have to be true in this problem. So if I could, let's say, and again, it doesn't really matter what we solve for. We're ultimately trying to find the value of b here, so I guess I would probably solve for x. And like I said, it really doesn't matter which one we do. We could get, we did our 12x equals -2b over here. I guess I'd probably solve for b, since it'd be nicer numbers to work with, no fractions. So it'd be -6x squared equals b. If I take that -6x squared and I plug it into the top equation here, I'd have 4x cubed plus 2 times -6x squared times x plus 8 equals 0. And ultimately this turns out to be cubic, which is nice because it'll combine with the other cubic. So this ends up being -12x cubed So we'd have negative 8x cubed plus 8 equals 0. And keep in mind here that this is a non-calculator problem, so the numbers are generally going to work out fairly nice. Okay. So if we subtract, we're going to wind up with 1 on that side. So what do we get for x? 1. However, are we looking for x? No, we're not looking for x. So don't pick C, because we're not looking for x, we're looking for b. So plug that 1 back in for x here in your b equation. We get negative 6 equals b, which ultimately is letter A. Questions on number 8. Next. Mike?
Number 9.
All right, number 9 says, what are the equations for the horizontal tangents of the graph of y equals 4 e to the x plus 7, and then e to the x minus 1 on the bottom. And it says, yeah, ultimately we just have to find the equations for the horizontal asymptotes for this graph. So if the equation that we have here is 4 e to the x plus 7 and e to the x minus 1, and again, keep in mind that we're looking for horizontal asymptotes here. We're not looking for horizontal tangents. We're not going to find the derivative inside it equal to 0. Okay, we just want to know the horizontal tangents. Well, keep in mind that when we get horizontal tangents, those are going to occur when we have limits as x approaches infinity, or when x approaches negative infinity. That's what creates horizontal tangents. Okay? So ultimately, we just want to find the limits as we approach infinity. So let's think about what's going to happen with these two functions here, knowing what we know about power functions. If I have e to the x and I have plus 7 and minus 1 here, ultimately at infinity, what the plus 7 and the minus 1, are they really going to do anything in terms of changing the value? Pretty much the same at infinity. We got gigantic numbers. They're not going to, the plus 7 and the minus 1 aren't going to change. So really, what do we have here? We have 4 e to the x over e to the x. So what is the, it's going to behave like what? It's going to behave like 4. So at infinity, no matter what I put in here for x, I'm going to have 4 times on top and 1 on the bottom. So ultimately, it's going to behave like 4. These two functions are essentially going to be the same growth rate, aren't they? Okay. So therefore, what's my answer to this one? This is going to be 4. And if I do negative infinity, then what? Gotta be a little bit more careful with this one. Growing wise, they're going to grow the same. Okay? But decaying wise, if these are going to get smaller, remember these are both going to go to what at negative infinity? Both of these e to the x's. They're going to go to 0, aren't they? As we go to the left, these e to the x's are getting smaller. So really, these two are going to act like 0 at infinity. So really, what do we have left over? If we have 0 here, we'd have 7 and negative 1. We'd have negative 7, wouldn't we? So therefore, our 2 that we would have would be letter D. Should be 4 going to the right, negative 7 going to the left. I think it's a non-calculator problem, so you can't obviously you can't graph it and see for yourself. But ultimately, just think about what's going to happen if we let big numbers be in there and we let small numbers get in there. That's what's going to create horizontal asymptotes in any equation. What else?
I thought you used powers on horizontal asymptotes. Like, if the powers are equal, then you
Well, isn't that really kind of the same idea here? Aren't those powers equal, if you will?
yeah.
I mean, most of our work has been with polynomials, but ultimately these would be the same growth rate. Because they're both e functions. They're the same as one another. So it'd be like having x cubed and x cubed, basically. So still be 4 over 1.
But then where would you get the negative 7?
Well, again, ultimately these two functions, what is this going to do at negative infinity? This is going to go to 0. So what's going to be on top? This is going to be, think about it just from a straight limit standpoint. If I told you to give me the limit as x approaches negative infinity of just 4 e to the x plus 7, e to the x itself at negative infinity is going to be 0. So what's the answer to this? 7. One of the things we have in limits is we have a limit of a quotient. As long as the bottom doesn't equal 0, we can take the limit of the top and the limit of the bottom and just divide them, and that gives us our overall limit. So we can just find the two individuals as well. Same way. It's a little tougher with the infinity part because they both go to infinity. So there we'd have to recognize that they have the same growth rate because they're the same function essentially. What else? Yeah. 12, we have a graph here that says our g of x function is defined as 1 to x of f of t dt. So very similar to our problems that we've been working on in this last chapter. We got an integral defined function. In fact, I gave you a packet that there's a bunch of these on there too, integral defined functions to practice. But bottom line here is we want to know what are some of these values in relationship to each other. So the first value in question here is g of negative 4. So let's see if we can figure out what's g of negative 4. Okay, we have the information here in terms of what g is equal to. It's equal to the area under the f curve from 1 to x. So keep in mind that if we were to take that picture and we got 1, 0 as our point here, and it looks like negative 1 is our next point over here, and it goes through 2, 0, and then negative 4, 2. So we have ultimately that shape. So if we go left here and we find the area, if we find the area of that triangle right there, okay, that triangle is 1, 2, 3. So 1/2 times 3 base, 1 height. So that would be 3 halves. Now keep in mind that it's under the x-axis, so normally it would be negative, right? But what are we also doing here if we go from 1 to negative 4, negative anything, we're going backwards, right? So if that's negative and backwards, that makes it back to what? Makes it back to positive. So that value would be 3 halves plus, and then this value over here is a 2 by 2 triangle. So that right there would be straight up area-wise would be 2, but it's above, which makes it positive, but it's left, which makes it negative, and so ultimately it would be negative 2. So our final answer is going to be negative 1/2 then for g of negative 4. Okay. Questions on how we got either of those two? So again, straight up area-wise, those are my areas of my two triangle parts. Alright, how about g of negative 2 is the next point in question. We know g of negative 2 is this, which would be positive 3 halves. So far we know which one's bigger and which one's smaller between those two. Okay. Then g of 1 is the other one in question. What's g of 1? If I go from 1 to 1 of f of t dt, I'm going to get what? 0. And then finally, if I go g of 5, g of 5 is going to be, goes up to, looks like it goes up to 3, 1, and then down to 5, 0. So it would be that right there. Ultimately, that would be 1/2 times, going from 1 to 4, or 1 to 5 would be 4, and then up 1. So that would ultimately be 2. So my g of 5 would be 2. And the issue is, can we order those? Well, I hope so. So which one's the smallest? G of negative 4, which rules out everything but a and b at this point, right? And then the next smallest is g of 1, which is the 0. So it would have to be a only, would be the only choice. And just to double check, it should be g of negative 2, then g of 5 in that order. So corresponds with letter A. We're good to go. Next. Right. Okay, number 10, we got f of x here this time is equal to e to the x squared. And it tells us that at how many points in the closed interval, negative 3 to 3, does the instantaneous rate of change equal, or instantaneous rate of f equal the average rate of change? As soon as you read that, one theorem should come to your mind. That's the mean value theorem. Right? When does the derivative equal the slope between the endpoints? That's the instantaneous rate of change is the derivative. The average rate of change is the slope between the endpoints. So bottom line here for us then is that we need to take a look at if we're going from negative 3 to 3, let's figure out what we got here in terms of our y values so that we can calculate that slope between the endpoints. And so in our case, if we put a negative 3 in there, we're going to get e to the 9. And a 3 in there is going to also give us e to the 9. So ultimately, the slope between our endpoints is going to be e to the 9 minus e to the 9 over 3 minus negative 3, which ultimately doesn't really matter what the bottom is because we're going to get 0. So the slope between the endpoints is 0. Right? And we want to know, ultimately, when does the derivative equal that? So the derivative here would be itself times the derivative of the argument. So that would be your f prime. So we'd have 2x e to the x squared as our derivative. And ultimately, we want to know when does that equal 0. Well, think about this. If I have these two equations that are being multiplied, this is a zero product property problem. This times this equaling 0 would mean this equals 0. So 2x would have to equal 0, or e to the x squared would have to equal 0. Well, what do we know about this one? This is going to be true when x equals 0. And this is going to be true when? When does e to the x squared equal 0? Never. Right? It's an exponential function. No matter what we put in there, it's not going to equal 0, is it? So therefore, how many times does it equal 0? ones. Therefore, it should be letter B. Next, 1 through 15. Josh? 11, we've got another mean value theorem problem. Says this time our function is x cubed. What are all the values of c that satisfy the conclusion on negative 1 to 2? So just like we did the last problem here, we're going to go negative 1 and 2. Figure out negative 1 and 8. So if I go 8 minus negative 1 over 2 minus negative 1, we get 9 on top, 3 on the bottom. So the answer here is 3. And the derivative here is 3x squared. And we want to know when does the derivative equal the slope between the endpoints. So ultimately it'll be negative 1 and positive 1. Now, here's the issue that we have here is it both of these or is it just the one? Because you'll notice that there's both choices. Okay, 1's on there, and then negative 1 and 1 are on there. Okay? And so what I want you to do is take a look at your book because we want to make sure this is clear as part of the definition because this is kind of a trick, if you will, because we want to make sure that we know whether endpoints can be included because ultimately that's the issue. Can endpoints be included in this? And your mean value theorem was on page 186. So let's read and interpret and make a decision on whether endpoints can be included as our values of c. Okay? So ultimately it reads that if y equals f of x is a continuous at every point on the closed interval a to b, differentiable at every point on its interior a to b, then there is at least one point c on, there's your key right there, isn't it? Okay. What do they tell us about a and b? A and b is the open interval a, b. Okay. At which this is true. We already figured out the answers to this. The possible answers are negative 1 and 1. But what do we know about c? Is c part of this? Okay. If it's negative 1, it's not part of it. If it's 1, it is part of it. So the answer really is only just 1 only. Okay. So that means that endpoints are not included in our values of c. Okay. And therefore we should get b, which is 1 only. So good lesson there because it's kind of a subtle part to the mean value theorem that we often would probably get wrong if we didn't specifically study that part. When we find these c values, they have to be on the interior of the interval. They can't be endpoints. We've had several in the past where we get two answers and one of them's not even in the interval at all, and obviously that one's out. But if it's an endpoint, it's out too. What else? 13. We got x plus y equals xy, and we want to find the derivative. So what should we recognize immediately on this one? What kind of problem is it? So part of getting these problems right is the recognition part. Can't solve it for y, can we? So what kind of problem is it? It's an implicit differentiation problem. Okay. So as soon as you know that, then we know that the procedure then is to differentiate each piece with respect to x. So d dx of x is just 1. Okay. We know the derivative of y is going to be 1 also, but 1 dy dx, because anything that's in y is going to be a chain rule issue. Okay. And then on the right, you've got to recognize that we have what's going on the right. Product. So first times the derivative of the second, plus the second times the derivative of the first would yield that. And remember our strategy after we differentiate each piece with respect to x is to get the dy dx stuff on one side and the other stuff on the other. So we'd ultimately have dy dx over here minus x dy dx over here. And then over here we'd have y minus 1. And if we factor out a 1 minus x out of our dy dx over here, we get dy dx equals y minus 1 over 1 minus x. And let's check our choices and see if that's an option. Do we have a y minus 1 over 1 minus x? Nope. So the other option that we have then is manipulating this because we're pretty sure that our work is right, so don't give up just because it's not there. Okay, recognize that if you look at letter C, if I did 1 minus y and x minus 1, Okay, are those two equal to each other?
Sure.
And if so, why? Why are they equal? I mean, you could put some numbers in there and test it and see if they're equal, and they are. But okay. What did I do to get this into this? Did I just multiply by -1 over -1? And why is it okay to do that? Because what's -1 over -1? 1. So therefore, I didn't change anything, did I, by multiplying by 1? Just change the order. Next. Got differentiable functions f and g. 15. Got a velocity equation then. V of t is 8 minus 2t. T greater than or equal to 0, it says. The particle moves upward till it reaches the origin, then moves downward. It says the position of the particle at any given time is given by what? Well, our position equation, how is that related to velocity? And antiderivative, so 8t minus t squared plus c would be our answer then. True? Alright, so the issue is, how do we find c? Did they give us an initial position here? No, but what did they tell us that happens though in the problem? That it moves upward until it reaches the origin. Keep in mind it's a vertical motion problem. It's going up first to get to the origin. So let's think about where would it be then if it was going to have to move up to get to the origin. It would have to be below the x-axis. So what would be the only c? Obviously the only two choices here are a and b at this point. Okay, which c makes sense then for us? It wouldn't have to be a -16. Would it be the only one that would make sense? Positive 16 would put it above, wouldn't it? So therefore it would be t minus t squared minus 16 would be the only reasonable choice. What if they had given us a -16 as a choice and then like a -8? How would we have chosen between those two? We wouldn't have had means to, would we? So they wouldn't do that because they'd have to give us more information. There would have to been more information to find c. Okay. Ultimately, the key is that recognizing that our position would have to be below the x-axis here in order to have that information be true that they gave us.
How does it reach the origin if it's always greater than 0?
If what is always greater than 0?
T? Or is for velocity?
Well, time is greater than 0 here if t stands for time. I mean, ultimately, if I put, in this equation that I have here, it's an upside down parabola, right? So our position could be positive at some points, could be negative at other points. Upside down parabolas, could look something like that. The position could be negative here, but at time, whatever, it could be positive here or whatever. Others, 1 through 15.
14.
14, we have some integrals given, but we know in general that f of g of 4 minus f of g of 2. And we want to know which of the following definite integrals is equal to this. Well, keep in mind that when we use the fundamental theorem, we anti-differentiate, and we put in 4 and 2. This looks like the answer to an anti-differentiation problem, doesn't it? Okay. So it'd be pretty safe to put 4 and 2 there in those spots, wouldn't it? Okay. Which ultimately doesn't help us at all because they all have that. Okay. Okay. But the question is, what is this going to be? Well, remember, if we take a function and we anti-differentiate and get this, f of g of x, if you will, okay, then f of g of x is going to be like our big F. That's going to be our antiderivative. True? And so the question is, what goes in here? Well, in here would be the derivative then, wouldn't it? What this came from? Okay, well, what's the derivative of this? Well, the derivative of f of g of x is f prime at g of x times g prime of x, based on what rule? Simple chain rule problem, isn't it? We know that the chain rule, the derivative of any composition, is the outside function's derivative evaluated at the inside function times the derivative of the inside function. Okay. So therefore, which integral matches up correctly? Nope. Remember, this is our integral right here. So this right here would need to go here in order for us to get back to this as an antiderivative. So it should be letter D, shouldn't it? Others, 1 through 15. 1 through 15.